So we have done 4 lectures from this book, Understanding Machine Learning from Theory to Algorithms. So this is quite theoretical. I was told by Parsov that he doesn't see the topics taught like this in other courses. So perhaps because in this book there is also some proofs and so on, okay, guarantee and so on. So maybe that's why other courses may be applied, okay. So, so what we have seen so far, right? If we recall a little bit, right? Just to see where we are and where we are going, right? Quick recall of what we want to do and what we have done so far. So we are interested in machine learning, and in machine learning, usually what we are supposed to do is do some classifications, okay? So, and then I have some other class, and these could be represented by, let's say, some vectors in some space, okay, and this is some other vector in some space. So classification usually means that I will finding a function f that can separate one class from the other, okay. So this is a binary classification problem. So this is, let us say, it's class 1, okay, and this is class 0, okay, or you can say it's +1 or this is -1. So machine learning means learning this pattern, okay, based on the given data, that this set of data is +1 and this set of data is 0, okay. So this is called training data, where it's known to me that, so it could be, let us say, spam email and non-spam email. That could be one problem you have, that you get some emails and then based on certain features of the email you want to classify whether it's a spam email or not spam email, okay. Then it's a classification problem, and in this case the classes are 2, okay, spam or no spam, right. So now the training data will come in this form, where I will be given some samples of which type of data is spam or which is not, right. So let us say I have some data, okay. Let us say this data is x1, x2 and so on, okay. There is some data, it could be a vector, and then I say it is spam, okay, and then second data, and then it's a non-spam, okay. So this way some data is given to me, and based on this data I will learn a function that can separate these two classes, okay. Okay, so this will be the training phase of machine learning. So the learning part of machine learning is like finding this pattern that can do the separation of the data. So once you learn this, then the testing phase is when someone gives you a new email, okay, which was not seen before. So that email, based on the feature, it may lie here, let us say. So this is the new email, okay, represented as some vector, okay. Then since you have learned this function, you will see on which side of this function this is, right. So if this is on this side, then for the new data, so this is a training, and then during testing you have new data, let us say this way, and then you are supposed to predict whether it's a spam or no spam, okay. So this is a classification problem, okay, and many type of data can be represented as vectors, and you're supposed to find a boundary, decision boundary, or separating hyperplane, depending on whether it's linearly classified or not. So here, if I'm able to do it with a line, then it's linearly separable, and this one is like non-linearly separable, and so on. So many methods are there based on this. So this is a classification problem, and then we have regression problem, okay. So regression problem is a little bit different, where here I'm given a set of data, and in regression problem it's not about separating into classes, it's about fitting the data, okay. So regression problem is like this, okay. What is the best pattern or the function that can go through this set of data as closely as possible, okay. So let us say temperature predictions, right? So I have temperature at this time of the day, it's this temperature, at this time of the day is this temperature, and so on. Okay, so this could be used as a training data, some handful of samples that I have, and then I predict using this I predict come up with a function that fits the data as best as possible. And once I have that, then for any other intermediate time, you can go and look at the function value because you have learned the function. So for any given x now, any given new x, you can say, okay, this is the possible prediction at this time of the day. So machine learning broadly classifies into two types of problems. So this is called logistic regression problem. Okay, logistic regression. The name is a little bit confusing because this is also called like regression. Okay, so this is logistic regression and this is like simple regression. Okay, but a better way to say for this would be classification problem. So here you have certain number of classes. Here there were 2 classes, but then I could have multiple classes. So if I'm trying to predict from an image whether there are animals, so there could be like multiple animals. So there will be multiple classes in that case. So broadly problems go into, let's say, classification problem, or they go into regression problem. In regression problem, you are trying to learn a pattern, right? And it's kind of can give you values for continuous data, okay, like this. So you are predicting a pattern for the continuous real value data. In this case, the data, what you are going to predict is 0 or 1, okay? So these are kind of like discrete values. So either it's 0, 1, or it could be 10 classes, then it's 0 standing for cat, 1 standing for dog, 3 standing for horse, things like that, okay? So this is the main difference between this. So when I am training, given the data I have, then I would like to train certain model, right? Then I have to fix certain class of functions which may be suited for this classification or this regression, okay? So hence there is a concept of hypothesis class, okay? So this is something you are supposed to choose. One thing you can say is that I can have an hypothesis class that consists of all possible functions in the world, okay? Any possible functions, I will put it here, okay? So it's like all functions, so all functions f. So let us say if it's classification problem, then it goes from the feature space x to the classes 0, 1, okay? So I may do that, okay? And there will be problems if I do that, okay? If I allow all possible functions in the world so that they can do the classification and so on, or regression, there will be problem in the sense that it may try to memorize the data, okay? So this is a major problem in machine learning. Unlike any other area, there is something called overfitting, okay? So overfitting, let us say if I do it in this case, okay, we can also do it in this case, okay, both are fine. So let us first do it in this case. So given that I'm allowing all possible functions, right, and even forget that, if let us say even if I allow only polynomials also, then it may happen that there will be a polynomial that will surely pass through all this, okay? And this polynomial could be, let us say, 5th degree, okay? Theta 5, x5, theta 1, x5 plus theta 2, x4 plus theta 3, x3 plus theta 3, 4, okay, yeah, x2 plus theta 5x plus theta 6. So this is the polynomial that I thought of, and this polynomial fits the data very well. But the problem with this is that during testing, it may happen that it has done a bit too much. Okay, so it may be, it was possible to fit it with let us say a quadratic, which might go like this. Okay, okay. So in this case, I have used a very powerful model, and it goes through all the possible data, but then it will in many cases it will lead to memorization. So if it was not necessarily a cubic, quintic fifth degree, then this data point could have been, let us say, here. Okay, but then during training, the way I learnt it, it will now start predicting this, which is a big error. So specifically for Ankita, we are revising this a little bit very quickly. So why, there you may end up, what I'm saying, you may end up as a, even if it's fourth degree, right? What might happen is, let's see again. Okay, let us see again. Let us say these points are there. Okay, it may happen that the fourth degree can do this. Okay, so let us say this. But it may happen that the fourth degree fits the data well. Perfect. But if fourth degree fits, fifth degree certainly fits. Okay, it has more flexibility and so on. So fifth degree also may fit, but it might do a lot of, like this. It can also happen that 10th degree might fit, but 10th degree oscillates even more. Okay, like this. So this is our fourth degree, this is our fifth degree, and this is our sixth degree. Okay, so what machine learning tells you is you should be careful about which models you are using to fit. Okay, if it is not okay just to fit the data. Okay, because during training there will be many possibilities of fitting the data, but you should not overfit, like you should not do too much. Why? Because now let us say this, with the fourth degree we had this curve, right? I don't know if I have colors. I think I bought some colors also. Red is okay, right? So this is our fourth degree. You can be a little bit greedy and say, because this is something you decide in advance, right? You see a data and say, oh, I'm thinking of fourth degree or fifth degree, okay, something like that. Okay, you can do validation also, but as a first step you will say, okay, let me try that. And so it may happen that you try fifth degree, okay, or sixth degree, something like that, and when you train it will give you 0 error because it goes through all the data points. But the problem happens during testing, because let us say I have this pattern, but a new data comes, right? Okay, so this is specifically for Ankita because initially these things are not very easy to grasp. Okay, so let us say new data comes, because in machine learning you predict on new. You have to do that. That's what machine learning is about, right? You have to predict on new data. So let us say new data is here. Let us say new data is y. On y, okay, the actual data pattern was fourth degree, okay, and which should have been this. Okay, so actual data was supposed to have a pattern of fourth degree, but during training you went with, let us say, the 10th degree. Now you see, you are predicting this now. You are predicting this now. During testing you are predicting this. You see how much error you are making, right? This is called overfitting. Overfitting is when you impose a very powerful model to train a data which is simplistic. So during training everything looks perfect, 0 error, but then what matters is during testing how good predictions you are making. So what you are supposed to do, in fact this is the major problem, a major thing in machine learning. There are many powerful functions that can learn any amount of data. That's not a big deal. The big deal is to prevent overfitting. Okay, I can throw in very complicated model and it will learn the pattern in the data for sure, but the major problem in machine learning is to prevent this problem in the predictions. Okay. So keeping a model parameter which is good enough, small enough, and fits the data and does not do bad on the test data. That's the main challenge, okay, in machine learning. So so with this initial introduction, we are trying to kind of take an overview today, but it's not like we will do only overview, but we have done many things now. Okay, we have pack learning, agnostic pack learning, uniform. We want to see where all this stands and what could be done as a next step. Okay, so then we will prove something called no free lunch theorem. And no free lunch theorem is easy to state that it says that there is no universal learner that works for all the task. Okay, there is a difference. It's not contradictory to what I said just now. Okay, what I said just now is that given a task, I can learn it well, but I cannot have a learning algorithm which works for all possible tasks. Okay, so having one single thing to rule all does not happen, but given any task or function approximation, we have models that can work for a given task. Okay, so that's what no free lunch theorem says, is that you have to work hard for every given problem. Okay, find a new model, but obviously that model will be there. There are powerful function approximate that can approximate anything, but that will fail on some other task for sure. That's what no free lunch theorem says. Okay, so so this is what we will prove today, and this is quite interesting proof. But before that, but before that, what we can do is quickly review what pack learning, agnostic pack learning, which is where, and so on. Okay, so I have a machine learning problem, and then one of the questions is, right, how do I train, right? So I said that given the data, I can train, right? So for instance here, right, given a set of data, I can train, right? So training would involve, in this case, let us say, these are the set of functions I have. Okay, so in this case, let us say I have, let us say I go with the cubic, right? So theta x3, theta 2, x2 plus theta 3x plus theta 4. So I choose this model and then say, okay, at the first point, my output, let us say, are the z-axis, let us say. So at the first point, I have x1, and this must be some z1. Let us say this is z1, this is z2, and so on, right? So this is what I want, right? This may not be exactly equal, but I want that, right? For the second data point, z2, and so on, right? For as many data points you have, so let us say there are m data points, so then there will be m of these equations. And then I'm supposed to solve this. These x1, x2, x3 are all known, okay? And theta i's are the variables that I'm supposed to solve for. So I collect the known ones in a matrix A. So in this case, it's like x1 cube, x1 square, x1 1, x2 cube, x2 square, x2 1, and so on. And the unknowns are the theta 1, theta 2, theta 3, theta 4. And the outputs are the z1, z2, z3, z4. So this essentially becomes a linear system. But as I said, it does not have to necessarily exactly fit the data. So you can say that it's approximately. So this will be kind of in a least square sense. I want to minimize this difference. Okay. So we know from numerical linear algebra what are the ways to solve this. Okay. Essentially there are three ways: normal equations, QR method, SVD. Okay. So these are like the direct methods I'm talking about: normal equations, QR method, SVD. So this is an example where so solving this minimization problem is your training phase. Okay, So in this case, let us say it's theta, vector theta this. Okay. So this is called training. Based on the given data, okay, you formed a loss function and then you are minimizing this loss function over the variable theta. Okay. So this is one of the loss functions, right? Now if I am doing a classification problem, then the loss function will be on how many on how many of these data I am doing a let us say a bad prediction. Okay, so in how many cases? So let us say this is my function h, right? Theta of x. So in this case also I will have some function, this guy, which is s theta of x. Okay, and based on this I will say, okay, h of x for this must be 1, and h of some of these points here it must be 0. Okay, so that way I know how to kind of create a loss. Okay, so I can explicitly define this loss here. So this is set of all I in the training data m such that hxi is not equal to yi divided by m. Okay, so this is our prediction function, right? So, and this is a classification problem, and the classes are given by yi. Okay, for xi the classification is given by yi. So the loss is characterized as how many xi's you are failing to predict correctly yi, and divided by m. So this is essentially giving you some normalized loss. Okay, so divided by m total, and then in how many you didn't do the prediction correctly. Okay, so this is the loss function we use in this class since the beginning. Okay, and S here stands for sample. Okay, so samples in this case there are like m samples. So in this case, if you want to see in terms of here, so there are like these many samples are there. Okay, but these samples could be anything, as I said. It could represent a high dimensional one. Okay, so in this case these are scalar valued, but samples could be vector for images, it could be text, and you can say the classification of the text. So this text is about news, this text is about sports, so this could be your classification. Okay, so you can tag the data. Okay, so these are your samples. Okay, so on how many samples you are not predicting correctly, divide by the total number of samples. This is our loss. Okay, so and so this is the loss over the training, because this S stands for samples. So this I is all coming from samples. Okay, because M are the given data for us, labeled data. This is called labeled data. For each X I have some labels, right? So that's why it's a loss over the training data. Okay, but then I can also define the loss which I may incur during testing, like here. So for a new data comes, okay, I predicted this, and the original prediction should have been there. So this loss we can define it as a true loss. Okay, and this we can call it an empirical loss, or the numerical loss, or the loss based on the data we have, right? So this is empirical loss. Empirical means numerical. Okay, empirical loss, or sometimes it's called empirical risk. But the true loss is when I compute on the original distribution. Okay, so in this case it's on the sample, so the true loss is given like this. Okay, LDH. So the function that I learned on the true data distribution. Okay, but this true data distribution I don't know. Okay, how this data is distributed I don't know. Okay, so this is your true. So sometimes it's called risk. Okay, or test error, or so what this we may minimize based on the data I have, and then hope that this will be minimized as well, which is the actual distribution over which I am calculating the loss. Okay, So one way to validate your training, your machine learning model, is that although you have the M samples, but during training you don't use all the M. Okay. So let us say I have M samples total. Out of this, I do a splitting of let us say K, and remaining M minus K. Okay. And I train only on the K. Okay. By doing this, by keeping this some of the data away, this can help me in checking the error, the true error, because this will be the data on which I will not train. I will not show to the model, the training algorithm, what other possible data could be. So I will train only on the K. I learn the H, okay, and I minimize the training error. Okay, whatever H I have, I will minimize with that. So that will be the optimization problem where I will minimize this loss, and that's why we are doing optimization methods also. So that goes in there, and this is the true loss, and this will be evaluated on the test data. Okay, so this is where, so I can do this now. I can modify this to I in K, and these indices are going into M minus K. Okay, so here I in M minus K, the remaining samples. So this will serve as a true. Okay, this will give me some way to validate my learned model. Okay, if this error is small but this error is big, I will go back and I will change the H, because although this H is giving me error, but this is giving me less error, this is giving me high test error, so I should go back and find a better H for which this as well as this remains small. Okay, so this is how you can practically implement a machine learning algorithm. So from theory point of view, what matters is this loss over the samples, and this is loss over the actual distribution, which in practice we don't know, but in general we don't know, but in practice we keep some data hidden that can help us during validation. Okay, so this is an very short overview, and so here if I'm going to minimize an H, right, then I need to solve an optimization problem, argmin of LSH. Okay, so given the set of H possibilities I have, I will use an optimization problem, because this is a loss function. So we will minimize this over possible H. Okay, and then so this is the training error. So I will minimize this, and we'll look for which H it gets minimized, and the optimal one we call it HS. So HS is the best possible hypothesis that you get from the given sample. Okay, it may change for sample to sample. Okay, so that's our HS. So these are the main notations I have. Right. So what we have done so far is we have proved certain guarantee, and these guarantees come from some of the assumptions, because this is a very complicated problem, but in general you cannot really prove things without assumptions. So one of the things we have done is, so if you look here, right, one of the things we have done, so the question is like, can you prove a guarantee that this is below epsilon? Okay, this error is below epsilon. Okay, so this is a very fundamental question, right? I have a given task and I develop certain algorithm, okay, where I get some HS. Then what is the guarantee that this will be below certain accuracy epsilon? Okay, so we have proved results where we assumed in one of the proofs we assumed that there will be an HS which exist in my given hypothesis class. Okay, so these are the set of functions where I'm looking for where I'm looking for to minimize the training error. So one of the things we proved is yeah, even before that, so just continuing with what we did here, there is a problem of overfitting. Okay, there is a problem of overfitting. So what do we do to prevent overfitting? So that's one thing we noticed already. There is a problem of overfitting, and why overfitting happened? Because I allowed arbitrarily many functions in my hypothesis class. Okay, so one of the reasons of overfitting is that I allowed many functions in my hypothesis class. Okay, so one of the intuitions we get from here, okay, is that why can't to prevent overfitting, perhaps we have to reduce the size of the hypothesis class. Okay, so these are the set of functions in my hypothesis class, and one of the intuitions we get by looking at the overfitting is that this is finite. Okay, the number of functions in my hypothesis class is finite. By doing this, you are in a risk that you are restricting number of functions to choose from during fitting is so small that it will not fit well anyway, right? That's one problem. That's one problem also. Okay, if I say that okay, you are allowed only linear functions, okay, but then a linear function will do bad, right? Because linear function will be like this. So it's not fitting the training data well. Okay, that's another problem. I cannot shrink the hypothesis class very small, because then the training error as well as the test error will be bad. On the other hand, as we just saw, I cannot allow the hypothesis class to be very big also, because if I do that, then during training I may fetch a H which is very bad. Okay, so it starts overfitting. Okay, so what do we do now, right? One thing is sure, for overfitting I need to fix the size of the hypothesis class. I cannot allow arbitrarily many functions there. But if I do that, I need something more also. What do I need more? I need also that there is an existence of H which does fit the given data. Okay, so these are assumptions. These are not practical assumptions. Okay, these are theoretical assumptions I am saying. Okay, so although I need this because I cannot allow arbitrarily many functions for sure, but then if I fix this, as I said, only linear, then I do bad in both ways, training, test, everywhere I go wrong. So another assumption I have to use is something called realizability assumption, and that assumption says that although it's finite, but I do want to assume that my choice of class is such that one of the function does fit the data very well. Okay, so and this assumption is not just about fitting the data very well. This assumption is also about the true distribution. Okay, so there exists an H for which even the true distribution is like very, I mean, all these are not very realistic assumptions, but theoretical. Okay, so there exists an H in H such that LD of H is 0. Okay, so what I am saying is that too many functions not possible, overfitting very likely happening there, then I must choose a finite one, but then in my class I want to be lucky that the ideal H that I am looking for is there. Okay, so this is one possibility to guarantee. Okay, why this is a guarantee now? Because there is an existence of H now, and which again there is another level of difficulty. Which optimization method you use? Will this optimization method lose this H? Okay, so machine learning problem has many level of difficulty. Even not just this, another level of difficulty is the samples that you were given. The sample itself may not be representative. Okay, So that's why it's not an easy problem to put in a theory. Okay. Now why samples also matter? Samples matter because let us say I remove a point which was critical for choosing a, let us say, a quadratic, and removing that point essentially makes it linear. Okay. So let us say this set of points were there. Let us say this set of points were there, right? And these points were there, and I believe this point was there. Okay. And let us say I remove, why sample matters, right? So let us say I remove this point, right? So I got this sample now, okay, and instead of this sample, so this is not there in my training data. Okay. So with this sample, okay, for the same problem, with this sample, the optimizer will see the sample and then it will pick this H for us. Okay. Okay, let us use orange itself. So this sample for us, which is essentially linear. So sample played a role here also. Okay. You were unlucky to get a sample that was not a true representative, because if this sample was seen in the training data, you would have learned a better optimizer, which could have been quadratic or cubic. The fact that the sample itself was bad led you to get a hypothesis. Here, there is not a problem of optimizer. Optimizer has no fault. We cannot blame the optimizer. Here, the blame goes to the sample. Sample did not show us the true. I mean, it cannot show all the distribution, but it did not show the true representative of the data. Okay, of the distribution. So there are multiple level of difficulty. Okay, so when we propose a theory, then we also have to show that with a probability of choosing a sample, okay, within certain delta. Okay, so we also characterize that. So we should not get a bad sample. So let us have a probability that, okay, the sample doesn't go bad, and the hypothesis class is limited, and there exists a ideal H. Okay, in my training, in my hypothesis class, which will be used in the training. Okay, but this guy is good in the real test case also. Okay, which is perfect, because if this is good in the test, it should be good in the training, because training is a subset of the test. So training is coming, the sample is also coming from the distribution D, so H should do well also there. So this was our first line of proposal, that given a machine learning problem with this set of hypothesis class, samples can be characterized the bound for the LDH. Okay, so this is one possibility. Okay, so with this we had a theorem. This was the chapter 2 of that, and so I will just write the statement of this theorem, so with this idea in mind, we will just capture this in a corollary, which is in the book also. So this is corollary 2.3. So what it says is that let H be the finite hypothesis class. Okay, so H be finite hypothesis class. Okay, so that was already, like we said that it was supposed to be. And let delta, this delta corresponds to the sample. Okay, so I will write few lines more about delta, but let me first write down that delta belongs to 0, 1, because it's a probability value. Okay, and where delta, I will write down exactly what delta means. This is the probability of getting a non-representative sample. Okay, a non-representative sample. So if delta is the probability of getting a non-representative sample, then 1 minus delta will denote our confidence. Okay, the negation of non-representative is like getting bad, and 1 minus of that is like how good I will be. So the negative, the complement of this will be our confidence that we choose a sample which is good. Okay, so that's why machine learning is a difficult problem, I'm saying, right? Because there are many ways you can go wrong. Okay, so this delta has to be characterized. That represents for a sample which we usually denote by S. Okay, so that's our delta, and then n some accuracy parameter which we want our true error to be less than epsilon, right? So that epsilon is there, and this will be like any epsilon greater than 0, right? It's just like in maths you do prove continuity or something. So given epsilon, there exists a delta such that so on. So here in this case, we are trying to prove that LDH is bounded, can be made arbitrarily small. Okay, but in this kind of proofs, unlike in the real analysis case, you also have these guys probabilistic assumptions coming there, because things can go wrong for sure. Okay, there is no absolute guarantee. As I said, you give me only 2 samples, certainly I will learn something bad. There is no way I will come up with a good hypothesis. So this like we are dependent on the sample chance and things like that. Okay, so it can go wrong. So there is this probability argument here, and then if things go well, then I can go and reduce beyond certain epsilon accuracy, right? So this epsilon greater than 0, and let m be an integer. Now this m is the sample size, sample complexity, it is said. So how big? So there must be a bound on that also, like it should be minimum that much, right? So as I said, if I remove this, then I was doing bad, right? So there must be some bound on like minimum samples I need, right? So that m should be lower bounded by something here like log of. So these derivations we did. For the moment, you only have to understand how, what these mean, not necessarily the proof. So the bound on m, the sample complexity, you must have this many sample. So from here you can already see, if you want very good accuracy, meaning epsilon very small, then you have to take many samples. Obviously, infinitely many sample will mean that I will find the best H. Okay, that makes sense, right? So, but this is indeed more the accuracy you want, meaning epsilon greater than 0, and this epsilon essentially is about bounding this. So what we want is LDH is less than epsilon. Okay, so certainly you have to pay, you have to seek better and better size sample, and also H. You see the size of the H also matters here. Okay, so if the size of the H is growing, okay, but then also your m is supposed to grow. Okay, and there is also dependence on the delta. Okay, so delta being big means what? Delta being big means I am getting into a very bad sample. Delta big means this is small. Okay, and does it like make it bad or worse? Like if delta is big, what is going on with delta, right? So if delta is big, meaning my probability of getting a non-representative sample is very high. The probability of getting non-representative sample is very high. Then this, but again, yeah, it is between 0 and 1, right? This it won't, yeah. So yeah, this is between 0 and 1. I mean, at 1, if I get a very non-representative sample, right, delta, the probability of getting a non-representative sample is very high. So in that case, delta will be 1. If delta is 1, then it is m greater than log h. Okay, so essentially, yeah, it only depends mostly on the size of the h and epsilon. If delta is 0, 0 would mean probability of getting non-representative sample is 0. Probability of getting non-representative sample is 0, then why should m should be very high? There is something missing here, right? Let's see if we made any mistake in the delta denotes probability of getting a non-representative sample. So if delta is 0, then probability of getting non-representative sample is very low. So if the probability of getting non-representative sample is very low, this is very high, and log of infinity is infinity. So I am forced to have very large sample. I mean, let us say for a given problem, training data that is given to me, it may be small, but still it's a very good representative. Yeah, so if delta is 0, then probability of getting non-representative sample is 0. This means if delta is 0, then what it means is that the probability of getting a non-representative sample is 0, meaning I have very good sample, perfect sample. But if it is a perfect sample, then what Sukhinder is saying, it's essentially your true all distribution, right? Okay, if it's all distribution, still why should I have sample? Yeah, so if delta is 1, then it's like useless sample. Okay, it's like non-representative, completely non-representative. So this, the whole sample is bad. But then this inequality says pick something, right? Okay. Yeah, this is like still pick something. Okay. But one thing you should remember, all this is there, but we have not looked at the loss yet. Loss has deltas there also. Okay. So so even if you pick this, okay, your loss should be very bad. Okay, at some point, right? So let us write down the full statement, and then I mean, yeah, let us write down the full statement, and then yeah. So m should be the minimum number of samples, should be lower bounded by this. Okay, and then yes, and then for any labeling function, for any labeling function f, and for any distribution d for which realizability assumption holds, so realizability assumption, as I said, there exists an h in the hypothesis class such that LDF of h is 0. Okay, so meaning I have a very optimal h. So realizability assumption holds with probability of okay, and then with probability of at least, so this is like comma here, so with probability of at least 1 minus delta over the choice of IID samples, sample S, okay, of size m. I have to do it here. Samples S of size m. We have for every ERM hypothesis. This ERM also will play a role later on. So ERM is one possible learning, let us say, algorithm. Even that may be changed later. Okay, so we will come to that. So we have for every ERM hypothesis, HS, it holds that LDF HS is less than or equal to epsilon. That's it. This was our first result. Okay. Okay, this question still remains. In the agnostic case, we have this delta also inside the loss, but okay, that's fine. Okay, so yeah, this is our first result. So in this case, these are the assumptions we have. Okay, this is still bothering me. So yeah, if delta is 1, then I get a very bad sample. Okay. If I get a bad sample, then how come with m greater than, like let us say m greater than something, like at least how come I will have m lower bounded by something and I ensure less than epsilon? Yes, yes. I think what we are supposed to write is more. Okay. So this is with because the delta you insert it here itself. Okay. This happens with confidence 1 minus delta, which is very low. Yeah. Because your delta is 1. Okay. With confidence, yeah. So we have to be a little bit careful with this. With this confidence 1 minus delta. Now your confidence is 0 that its error is less than epsilon. We have to be a little bit careful compared to so okay. So now let us do this again. In a machine learning problem, there is a problem of overfitting when my hypothesis class allow them to run over all possible functions. We restrict that. So that's when h is finite. Delta is a confidence parameter. So again, like sample, we need some confidence on the sample we have. So this denotes that. But delta itself denotes representative and non-representative sample. Okay, delta denotes non-representative sample, and 1 minus delta is our confidence that the sample is good. So delta being 1 means it's a purely bad sample, then our confidence is 0. Okay, confidence of whatever we do from here points onward is 0. You do all this, m greater than something, but the fact that your error is less than epsilon, confidence is 0. This essentially does not happen. Okay, in probability, right? So then, and then we can also see the other boundary case when delta is 0, meaning I don't get a, the probability of getting a non-representative sample is 0, meaning the sample is the perfect one. The sample is perfect one, all this still holds, okay, and then my confidence that LDF, the true error is less than epsilon is 1, okay, because delta is 0. I never got any bad sample. This was the best sample I could have. So the error could be made arbitrarily less than epsilon, because epsilon is like any epsilon. You can choose any epsilon close to 0, and that I can make it arbitrarily less than this. But from practical point of view, then m will be like very, very large. Okay. Look, another way to say is that this may be not the best possible bound. Okay. This is one of the bound. Okay. We may make it tighter, we may make it better, okay, as we go into advanced and stuff and so on. But this is one possibility, but this is like a extreme possibility where we will say, okay, m should be infinite. Okay. If the delta is like the sample is the best one, then m theoretically it says like m may be like infinite. Okay. So yeah, so as I said, one may work a little bit on this. This is just our first result. In practice, we may not need infinite. Okay, so this was our first result. Okay, and the second result is second result comes from the fact that why did we assume that there exists an optimal h? So let us say this h is like h star. Okay, so there was an optimal h that exists in my choice of hypothesis class, for which the true error is certainly going to be 0. So the second set of results is about getting away with this this assumption, realizability assumption. Okay, so the second set of theory results says that can I get rid of this? Okay, so removing the realizability assumption, you go to, so this is called pack learning, probably approximately correct. So as the name suggests, right, it is approximately correct, but with a probably, okay. So that's why it's called probably approximately correct. This is like the approximately part, and this is the probability part. So in this, unlike real analysis where you just stop here you say it is approximately correct because it satisfies this, but still with some probability. That's why you call probably approximately correct. So this overall framework is called pack learning. So if you develop an algorithm or something like that, new algorithm, in fact in machine learning you come with whole set of things, right? Given a problem, type of data set, so you will fit all this and maybe prove some guarantee like this in a paper, okay? So this is called pack learning, and agnostic pack learning is when I get rid of this, which seems to be a strong assumption that in my choice of this class I had this optimal H star sitting there. So from optimization point of view, I did not want any trouble, okay? I thought once H star is there, optimizer will kind of figure out, provided I have good sample, obviously. So the another set of result is via removing the realizability assumption. So, but then as you can see, if I remove this, I can do very bad also, right? If I remove this, then what is the guarantee that, because H good one may not be there. So what they do is that they bring the concept of uniform convergence. Just like in maths, in sequence of functions, we have uniform convergence. So they borrow the idea from there. In uniform convergence, I have a pointwise limit of a function f, and I have a sequence of functions fn. Okay, I have a sequence of functions fn. Then uniform convergence is about whether my function fn goes to f, okay, or the difference is less than epsilon. For n greater than equal to some capital N, for n large enough, can I put this in a within epsilon tube, right? For all x, okay. So this is my x axis, right? So in real analysis, we say a sequence of functions fn converges to its pointwise limit f if the difference of this is less than epsilon for any given epsilon. Obviously, this n will depend on that. If you want better lower and lower epsilon, obviously your n is going to be bigger. So maybe I can put a dependence on epsilon like this. And this is for all x, and that's where we call it uniform, because it's uniform over all x. Once you have chosen n, then for that n onwards, for all x, they are within epsilon distance from the pointwise limit f. Okay, so they borrow this concept to get rid of the realizability assumption. So now what they will say is that, let us say an ideal function f, let us say, which is the label function in machine learning. Let's say labeling function is the ideal function, right? So if I have a new image of a cat, and then during this label function tells me, okay, this is cat or not. So this label function is also hypothetical, because this is what exactly we are trying to learn, right? So we can say that the true function that does all this is f, okay, which is the label function, and this is what we are actually trying to know, okay? So let us say that function is f, and then in this, what we will do, we will assume something like that. So we will assume that our functions fn are like L, and let us say finiteness of hypothesis class is still needed. So if the finiteness of hypothesis class is there, I can make a sequence of these Hn. Okay, so or essentially you can make a sequence of Ln. Okay, so this is your Ln, and then this H serves like your X here. Okay. Okay. So and then this error could be your 0. Okay, the 0 would be the ideal pointwise limit, and this Ln, yeah. So for different H, okay, this is my different loss function, right? So I'm not sure about the notations I'm using right now. In the book, I should not deviate much, right? So what did they use for in the uniform continuity? I will use exactly that. Yeah, uniform convergence. yeah. So yeah. So the yeah. So this f is essentially LDH, right? So the pointwise limit for us is LDH, and this is our LSH. Okay. So so we will remove this realizability assumption that there exists an optimal H, but what we are saying is that all the H I have are such that LSH from LDH, which is the true loss, are within the epsilon distance, okay, within the epsilon tube, okay, and the uniformness comes from the fact that this H is all the H from the hypothesis. Okay, so what they call it uniform is like this: for all H in H, LSH minus LDH is less than epsilon. Okay, so just like in the uniform convergence for sequence of functions, you do it for all X. Here you do it for all H. Okay, there is no such thing like this. We are saying here we don't have this. We are saying for all n. Okay, essentially. So here the difference here is that we are saying it for all H in H. We are not saying the H from certain point onward like in the sequence we do, but here it's like all H. So you can forget this. So they remove this part. Okay, so it's like for all H, LSH minus LDH. So from the true error, it's bounded by epsilon. Okay. So what you did now is that you said that your H earlier in your problem you would allow your H to be, so this is my ideal H star, and in the previous problem you said that H star itself is there in my hypothesis class, and some other hypothesis class could be very bad. They are very far from H and so on. But here you put a bound, right? Okay, here in this case you are essentially saying that H star is there, but any H that I have, they are within the epsilon tube. Okay, so it's like all the H are kind of well behaved, in the sense that they don't go far. Okay, you can say like this is another way of like, because this assumption also is quite strong, right? Like if you see this here, right, it's like as if I'm saying that that although I consider set of polynomials and ideally it was quadratic, so I am allowing maybe only up to third degree one, which will not go too far from here, and maybe linear one. Okay, so that all the functions I have are within the epsilon distance of this. Okay, so with this assumption, what it means is that all my functions are within epsilon distance of this. So in this case, I am saying that my choice of hypothesis class is such that all are within the epsilon distance. In the previous one, I said that there is an optimal one, surely there, but here I am not saying there is optimal one. Here I am saying all the functions H are good ones, but they may not be the best one. Okay, so that's where the concept of uniform convergence is used, where you kind of use the fact that all are good ones. So this is another way to do the same thing. Okay, the story doesn't change much. Yeah, in the proof there will be a little bit of difference, but we get a similar result like that. So what happens now is that everything is the same. Okay, the realizability assumption is changed. Okay, so this we got rid of this in something called agnostic PSE learning. Okay, so we can kind of just write the statement, and then we will prove today no free lunch theorem. So we are kind of like doing a review. So this is the chapter 4, which says that uniform convergence leads to pack learning with all these ingredients. Finiteness is there and so on. Okay, so I will just write down this corollary from chapter 4, which is the main result of this chapter. So this is H be finite. Okay, so let us just write this like this, H finite, and Z be a domain, and let H from, okay, so Z be a domain, and let L from H to Z 0 1 be a loss function. Yeah, I mean I could have written this. Okay, that's anywhere. Let us write this. Okay, so let L be a loss function. Then H enjoys uniform convergence property, with sample complexity m h epsilon delta is less than equal to log of 2 h by delta by 2 epsilon square. This is log. So in this case, what is interesting now, we are giving upper bound. Okay, so with this upper bound on the sample complexity, meaning the number of samples you are supposed to choose. Okay, so furthermore, class is agnostically PAC learnable. So agnostic refers to the fact that it's agnostic to the fact that there may not be the optimal one. Okay, so there may not be optimal H star. So that's what agnostic refers to here. Using ERM algo. So for all the detail of this, you can watch those videos. I'm just trying to make sense of what we have done, the major things so far. Okay, we have done a complete proof in the previous video, so you can watch those by epsilon square. So agnostic POC learnability is guaranteed with a upper bound on sample complexity. Okay, so that is kind of good, but again, one should be careful that all this happens with the confidence of hidden confidence of delta. Okay, so you may go ahead and say, if it's upper bound, then okay, I will choose it to be very small. Okay, so so this is agnostic POC learnability, and now we will do no free lunch theorem. Okay, so this is just with this we will stop today. Okay, no free lunch theorem. So this will be the new topic we will do. There are people who work on pure theory. I don't work on pure theory like this, but it's good to know this thing. Okay, you may not get a job by doing pure theory, but the industrial job may not be that much interested in pure theory, but it's good to know for better understanding. So there are people who spend whole life on just proving these things. Okay, so so there is this fifth chapter is bias complexity trade-off. So in the following chapters, what we will see is one of the things, as I said, is restrict the size of the hypothesis class to be finite, and we will see later that even that is not a necessary requirement, that there is something else that plays a role, not the finiteness of the hypothesis class. There is something else that may prevent overfitting. Okay, we should not blame it on the size of the hypothesis class. So we will see this in the next class. We need to define something called VZ dimension later on. So in that case, we say that even the finite hypothesis class are learnable. Okay, if something happens. Okay, so we will do that in the next class. But today, what we will do is there is no universal learner. Okay, so no one, we will prove that basically. Okay, so it's like no one can give you a learning algorithm that will be best that will be best for any task. Okay, So that's not possible. Okay? That's what we are supposed to prove today. So in words, this is the main thing. So no free lunch. So this is like a very famous words usually used in many places. There is no free lunch in many areas of many subjects. Okay, so there is no free lunch. Maybe you can search some topics in quantum computing. There will be something like no free lunch. In machine learning, there is no free lunch. In many other maths topics, you will say there is no free lunch. Okay, so I don't even remember so many, but I see like these are. So basically, it means like there is no universal guarantee or things like that. Okay, so yeah, so what this says is that no universal learner exists. No universal learner exists. Okay. The proof is quite involved in the sense like it will be puzzling to see how one could do a proof like this, but let's see. Okay. So I'm just trying to scan like is there anything important before the theorem. Yeah, let me write this one paragraph just before as a motivation before going to the theorem. So so no universal learner exists, and more precisely, the theorem states that for binary classification task, for every learner there exists a distribution on which it fails. We say that a learner fails. So what is the meaning of fails, right? So we are like trying to define. We say a learner fails if upon receiving IID examples, IID is independent and identically distributed, IID examples from that distribution. Basically the test error is bad. Okay, so from that distribution there exists from the distribution its output is likely to be is likely to have a large risk. By risk we mean the LDF. Okay, is likely to have large risk. Okay, so now I can straight away write the theorem, the no free lunch theorem, theorem 5.1, no free lunch. So let A be any learning algorithm for the task of binary classification with respect to 0-1 loss over a domain X let M be any number smaller than mod X by 2 is representing a training set. Then there exists a distribution D over x cross 0, 1 such that there exists a function f from x to 0, 1 with LDF equals to 0. So this is what this is saying is that there exists a perfect learner, but it's not the one you have in hand right now. Okay, so it will fail on some other D. That's what he's trying to say. Okay, so the second point is like about the failing. Okay, so with probability of at least 1 over 7, which is considered significant. Okay, so 1 over 7 over the choice of D over the choice of sample S coming from D, we have that. So we have that LD, which is our true loss. The error that we will make is at least 1 over 8, okay, which is significant because there exists a ideal learner which is F, which is making an error 0, and the learner that you have proposed, which is AS, via some algorithm A applied on the sample S, that is making a big error. Like 1 over 8 is considered big. Okay, so 1 over 8 with error, essentially you are failing. Basically, that's what it's trying to say. Okay, so let us read out this no freelance theorem. So what it says is that let A be any learning algo for the task of binary. So let us focus on binary because any other thing is essentially extension of binary. So if it fails on binary, then yeah, others will be even more problematic. So A be any learning algorithm, let us say for a simple task of binary classification, and let M be a number. Let M is the sample size, and that's the usual notation we use. So M essentially means the training sample size. Okay, so training sample size is less than mod x by 2. Okay, so the training sample I'm choosing is like half of mod x. Okay, then there exists a distribution D, okay, over this x 0 1. Okay, so the features and then labels, such that there exists an ideal learner for which the true error is 0, but with probability of at least 1 over 7. This is like the delta we were thinking of. So with the probability of at least 1 over 7 over the choice of the sample, we have that we will incur an error of at least 1 over 8. Okay, so what it's trying to say, there exists a distribution means there exists a problem. Okay, the D characterizes a problem. Okay, so the distribution means like a new problem. So what it's saying is like you have some learning algorithm that it learns from some sample S. Okay, then that learning algorithm or the method or whatever you can think of, if given there will exist some new problem, meaning there exists a distribution D. For that new problem, there is an ideal learner, but your method will give at least 1 by 8 error. So there exists a distribution means there exists a new problem where any given algorithm is supposed to fail. There will be no universal learner. Yeah, it is ERM. So far what we are doing is ERM. No, but there the distribution is fixed. Once the distribution is fixed, the problem is fixed. No, for a given problem, which will be a given distribution. I choose a sample that comes from that distribution. Okay, then yeah, because if I change a distribution, then it will be a new problem. Yeah, but we have to like specifically look into the statement, right? I mean, here we are saying there exists a distribution, meaning I will create a new problem, okay, over which there will be ideal, but then I won't do well. In the previous ones, we are given a task D, okay, a distribution of corresponding level function. Obviously, for that all this is 0, and the sample comes from the given D, okay, and yeah, the hypothesis is built on the D. I mean this, yeah. How will you pick a H which is very good? You only see sample only, right? Yeah, exactly. I mean there exists a D which for the moment it's ERM only. Okay, so let us fix that. So all are ERM. This has to do with the samples also. Okay, because you are shown half of that. You are shown half of that. So this new distribution that we have, that's playing trick on the other half, because of which things are getting spoiled here, okay, which will get spoiled here. So you may have a universal learner giving all the level data in the world, like LLM model or something like large language model or whatever we have, let us say. Everything is there in your hand. But during training, so X captures everything, like image classification, text classification, whatever you name it. But M, the training data, because at the end of the day, you can train only on finitely many samples. Okay, so let us pick M, which will be smaller than all possible things you have. So it's like mod X by 2. Then I will design a task using the remaining half that you have not seen. Okay, you were giving all the freedom of whatever hypothesis functions you are choosing. Okay, everything in hand. I mean, in terms of functions and so on, no restriction at all. But the fact is that you have not seen the other half of the sample. I will create a very interesting task for that other half, and that's where you will start failing. Okay, where you will make at least this error. So as a corollary, there is in fact one corollary just after this theorem. So in the case that H is infinite, which is a possibility, then H is not pack learnable thanks to like no freeness theorem. So X happens to be infinite. That seems to be like a special case of this. So I can write this corollary also already. And H be the set of all functions from X to 0, 1, then H is also not pack learnable. Okay, let me do a proof of this, and corollary will make sense after the proof, I think. So let us first prove this. Okay, sometimes we also understand things while proving. Okay, so let us go with the proof also, and then the proof is quite tricky. Okay, so let us see. Tricky in the sense like the very weird constructions are going on. Okay, so let us see this. So this theorem states that for every learner, so every learner will be shown half of the training samples. Okay, then there will be other half on which some interesting task is there and it fails. Okay, so that's what it says. So the theorem says that for every learner there exists a task on which it fails, even though the perfect learner is there, which is f, right? Even though that task can be learned by another learner, So in this case, the trivial learner, in this case, the trivial one is the function f itself. Okay, and also for the ERM case, we had some bound on m, right? That guarantees like certain epsilon accuracy and so on. Okay, so or more generally, ERM with respect to any finite hypothesis class that contains f in this case, in the no free lunch theorem, we did not guarantee that there exists an f which is there for the algorithm. We didn't guarantee that, and we didn't guarantee uniform convergence also. Okay, so ERM with respect to any finite hypothesis class that contains f and whose size satisfies m greater than equal to 8 log, so 7 by h by 6. Okay, so this was corollary 2.3. We have proved this before, that if we use an ERM with finite hypothesis class that contains f and whose size satisfies this, this is a proof we did corollary 2.3. Okay. So what is the difference between theorem 5.1 and this statement? This statement, let us say the more generally part. Let us start from here. Now what it is saying is that this task can be learned by the trivial learner, which is f, the label functions, or also more generally by ERM with respect to finite hypothesis class f whose size will satisfy m greater than, with sample complexity at least m, and if it's a finite hypothesis class, then ERM it will satisfy basically LDH less than epsilon. But what I'm trying to say is, what is it that no free lunch theorem says which is not there in this statement, ERM with finite hypothesis class that contains f? ERM says that there is a which is a learning algorithm, and it is shown m number of samples which is smaller than mod x by 2. Okay. Then it says there exists a distribution over which I will make a minimum possible error, which is in this case 1/8. But here we wrote a statement, right? There exists a trivial h. Okay, that's there, and then more generally ERM is with any finite hypothesis class that contains f and who satisfies this. But one of the strong assumptions is that it contains f, right? So it contains f, then ERM guarantees that, okay, with sample complexity or whatever. Okay, so but here it's not the, it's a statement that says that for half of the samples I am shown, I got the best f. Okay, let us say, by training or whatever. Okay, but then I created a new task where it doesn't work anymore. Okay, so that's what no free lunch theorem says. I hope it's, there is some that is about not having a universal learner. Okay, that's about having no universal learner. And yeah, and the things that we have proved just now is for a given task distributions. We have the sample probability and the realizability assumptions like that. Okay, in no free lunch theorem, what essentially means, if I'm not wrong, is this itself may not be guaranteed. It's not just H being fixed, it's also the samples that you are shown. Yeah, but new problem could be created in the other half, right? Which will be pretty. No, that's the thing, right? With the other half, I can create a problem. I will artificially create a problem task, which will no. In free lunch theorem, we don't fix H. H is about you have a free hand on any learning algorithm. Learning algorithm here means like, because learning algorithm here means that H must be anything that I'm. But the problem is that this best H that you are thinking of has seen only M, right? I mean, when you are optimizing, H is, yeah, I mean, yeah, so let us see what do you mean by H is fixed, right? So as an end result, what I'm thinking of is H is something, HU, let us say. Okay, so HU, that's it. Okay, now with all the samples in the world, right? So this is my X, and let us say this is my 0, 1 labels. But obviously H will get fixed for sure, right? What I'm saying is, like, given M samples I'm given, right? So what no free lunch theorem is telling is that you are given M number of samples, which is X by 2, and however large it is, okay, because X could be very large. What's saying is, like, you build a universal learner, HU, okay? So obviously this gets fixed for sure. I give you all the data in the world, okay, and I have all the label data in the world. I gave you only half of that. With that half of the data, you were allowed to choose train over that for over any H, and then you came up with saying to me and saying that this is what I got, HU, which is the best, I think, with the M samples that you gave me. This is my universal learner. You claim that, okay? You say that now this becomes fixed, obviously. This universal learner that you trained on M, this gets fixed. And now you are telling me, okay, this is my universal learner. Now I claim that you will give me any task, I will do very well on the test data. I will minimize very well. But then I will tell you that, okay, you come with a fixed learner HU after training, obviously. Then I'm saying that I will create a new task which is like D, over which your fixed HU will start making error. So this is fixed, obviously, but then while you are training, you are shown M, that's fine, and you are given all the functions in the world, but once you get this is fixed. After you have got fixed, then I will say, okay, now I will create a new problem on the remaining data. You will start making error. Okay, so let us try to prove this theorem. Okay, so I hope we got these differences that we have. Okay. So here, like, finite hypothesis class, realizability assumptions, for a distribution this happens. But here is a little bit different problem. Here you are allowed free hand, go do whatever you want, but you can never come to me with the saying that I have one best universal learner. Okay. Okay. So let us do a proof of proof. So let us define a set C, C be a subset of X, C be subset of X of size 2m. So that's exactly what the intuition is, right? So even the proof is saying that. The intuition of the proof is that any learning algorithm that observes only half of the instances in C has no information on what should be the level for the rest of the instances. Okay, so it's a good line to write. Okay, so intuition. This is what will build the proof. Okay, intuition of the proof. Okay. Intuition of the proof is that any learning algorithm, any learning algo that observes only half of the instances C has no information on what should be the levels of rest of the instances in C. Therefore, there exists a reality that is a target function f that would contradict the labels given by AS. Okay, the labels that AS predicts on unobserved instances in C. Instances, samples, all this same thing. Okay. Okay, note that there are, so let us now get into the main thing of the proof. So in words we also written this down for completeness, and then now let us build the proof. Okay, so note that how many functions are there from C to 0, 1, right? C to 0, 1. So basically from samples to the labels. Okay, so there are t equals 2 to the 2m, right? Functions from, so you're okay with this, 2 to the 2m, right? Because the size of C is 2m, so the number of functions that you can make from C to 0, 1 is 2m, right? Either it goes to 0 or 1, right? So then it's like 2 to the 2m. Okay. Denote these functions by f1, f2, ft. Okay, so let us say these are the functions. For each such function, let di be a distribution over C. So for each such function, let di be a distribution over C cross 0, 1 defined by di xy, and this is 1 by C if y equals to f I x is 0 otherwise. Okay, so we have built a distribution function here. So di over xy is 1 over c if y is f(ix) and 0 otherwise. Okay, so what is LDI fi, right? LDI, because the way we constructed it, LDI fi will be 0. Okay, so because it's kind of memorized in this case, right? So LDI fi is 0. So for this is the best distribution for the f, the way it's constructed, because it will do perfect prediction, because for a given x, it has the corresponding y, okay, and it will be 0 otherwise, okay, whenever y is not equal to fxi. So for all the samples, this is the perfect fi for the given di. Okay with this? Okay, I hope. Okay, so now we will show that for every algorithm A, yeah, so this is the main thing we will prove. So let us write down. So what we will prove, which will be essentially the proof of no free lunch as well. So what we will prove is that for every algorithm A that receives a training set of m examples from the label data 01, C01, and returns a self-claimed universal function, let's say as, from C to 01. It holds that. So this will make an error, which is I over t, and expectation of LDI ES is greater than or equal to 1 over 4. Okay, inside it's hidden that, what is hidden here inside is that it saw only m examples. It had 2m, and it saw only one m example, although the fi is constructed in a way that LDI was 0, but then the learned algorithm is now making error of at least 1 over 4. Okay, there is like equivalence of these things as well, like there are a few so let us write down the equivalence of this. So this means that for every algo A prime that receives a training set of m examples from x01, there exists f from x to 01 and a distribution D over x01 such that LD f equals to 0, and expectation of S dm LD A prime S 1 over 4. So why does this means this, right? The book has just written this. Did not say why. The book said that this means this. So what we will do for the moment is prove until here, and then we have to go to this. And the actual statement of the theorem is about LDS greater than or equal to 1 over 8. So there is a further reduction of this idea that gives you the final claim of the theorem, but the major result is like going up to here. Okay, so let us get until here and then look into this further reduction to here, and then the final reduction is here. Okay, so let us try to prove this first part. Okay, so so now let us prove this result first. Okay, so this in the book is 5.1. So there are k equals to 2m m possible sequences of m examples from C. How is that? I have to pick m. How many ways I can pick m, right? Out of this 2m, repetitions are allowed. Okay, then is 2m to the m. Okay, so repetitions are allowed. So that's fine. These many ways I can pick m sequences, repetitions allowed. So denote these sequences by, because this we have to allow this. Okay, the theorem says that out of all possible examples in the world, you are allowed to pick m, but it's also telling you pick any one you want. Okay, still you will come up with some d for which you will fail. Okay, so these are the possibilities I have, and so let us denote these sequences that we are going to pick by S1, S2 and so on. Okay, so denote these sequences by S1, S2, Sk, and if Sj is x1, xm, so if Sj is this, this is how, like there are m examples of that, then we denote Sij. One thing is like I can take m samples. I'm supposed to take m samples out of 2m, and another thing is like how many ways. That's not here. Like how many functions are possible from m to 0, 1, from these m samples to 0, 1. So the superscript I is for those level functions fi. Okay, so let me write this first. So Sji means on this sequence fi will be applied on these. Okay, so let us denote this by x1 fi x1. Okay, so these are the pairs x2 fi x2 and so on, and xm fi xm. So this is what this notation means. Sj and on Sj the ith f function is applied. If the distribution happens to be di, then fi correspond to the di, right? So then what you are receiving are these then the possible training sets you are supposed to receive are S1i, S2i and so on. Okay, because if it's di, then the functions that apply correspond to di are fi. Okay, then the possible sequences that you get So if the distribution is di, then possible training sets A can receive are SI1, SI2 and SIK, and all these training sets have the same probability of being sampled, and all these training sets have same probability of being sampled. Okay, there is no bias in this. So then we can write down the expectation of LDIAS. Okay, so let us write that. So expectation that S follows DM is LDI and AS, and this is, so it's like equal probability. So expectation will be like probability of 1 is 1 over k, right? So the expectation will be, the weights of the expectations will just 1 over k, the usual average, and then LDI A of Sij, and j equals 1 to k. Okay, so now I can compute the expectation of LDI AS, and this is like I, sorry, this is I. So for this, the possible samples I get are Si, okay, Sij, and j is like 1 to k, obviously. So the expected value of this is, yeah, sum of this. Now we will apply bounds on this. So this is what we wanted, right? 5.1 we have this LDI AS. So this is what we have written, and we are supposed to give a lower bound on this to be 1 over 4. So for a given DI, I have a corresponding Fi, and for this I have like m possibilities, I mean 2 to the 2m to the m possible ways of picking this these samples, right? So so we are trying to get an expected value of that, okay? And the expected value is like, on average I will do bad, like at least 1 over 4. Okay, I'm given a freedom to kind of like pick with my choice m samples in however way I want. Okay. Okay, so let us do a bound on this. Okay, because we need a bound on this. So basically this. So we will look into the max, because we look into the max of this, and here we have a max, right? So essentially bound on max of this, which is max of this. So max of this, so let us write down max of I in T. Yeah, so we do a max on I in T, right? And then 1 over k and sum of L di A of S ij. So the max of this, max is greater than the greater than without max, right? So this guy is greater than equal to, if I remove the max, it must be greater than this guy inside, right? So No, I mean, what we are going to use basically is max is greater than the average, and this average is over t. Okay, because this is max over t, right? Then what we are saying is like this is greater than the average over t. So average over t is 1 over t. Okay, and j equal 1 to k L di a s I j. Okay, so max is greater than the average. That's what we used. Max is greater than average. And we can interchange the sum. We keep the k sum out and t sum inside. So this is equal to 1 over k, j equal 1 to k, 1 over t, and I equal 1 over t, L di a s I j. So we interchange the sum of k and t, and this must be greater than mean over k. So this is now average over k. According to the outer sum, this quantity is average over k. So this should be greater than mean over k. Mean over j in k, 1 over t, sum I equal 1 to t, L di a s I j. Okay, so max is greater than average. That was the first inequality. Then we interchanged the sum. Then we said it looks like average over k, which should be greater than the mean over k. Okay, so these are simple inequalities. Next, fix some j in k. Okay, so fix some j in k. And denote Sj as x1 xm, and let us pick examples in C that did not appear in S. Okay, so let v1, v2, vp be the examples in C. Examples in C that don't appear in Sj. So clearly P greater than or equal to M. How? Why should P be greater than M or equal to M? So whenever in the book they write clearly, you have to be a little bit, in maths book they are always like this. Clearly, oh then okay, trouble. Yeah, but we are supposed to complete this, right? In I think in 15 minutes I will do. That's fine, like 15 minutes. Yeah. So either we say P is greater than or equal to M or M less than or equal to P. Or another way is like, why should M be less than or equal to P? What happened in the max part? So this is max over I, right? So max over I is greater than average over T. So this is average over T. Yeah, and then just interchange the sum, and then this is average over K, which should be greater than the mean over K, right? So max greater than average greater than mean. Max greater than average greater than mean. This is what we did. Okay, so therefore for every function f, every function h from C to 0, okay, so let us write down. Then therefore, so this implies for every function h from C to 0, 1 and every I, we have L di h is 1 over 2m, 1 hx is not equal to fix x in C. So this is like the definition, right? So how we define error of H. Okay. So this is by definition because the number of samples are R2, M, and C. Okay, and this one represents wherever this is not matching the prediction that you have and the prediction given by the level function Fi for the given distribution Di. So this is the definition of LDIH. Now this is greater than or equal to 1/2m, and so this is all over C, but then if I reduce the sum to P, right, so this is R equal 1 to P. So this number of sum is now lesser than, so hence it's lower. Okay, so 1 H VR not equal to Fi VR. Okay, so we have reduced this sum to R equals to 1 to P. So that's why it's less now, and in this we can so since P is greater than or equal to M, if I substitute M by P, it will make it even smaller. So this is less than or equal to 1/2P. Okay, R equal 1 to P, 1 H VR is not equal to Fi VR. Okay, the inside term remains the same, P greater than M, so this become lower. Okay, so hence 1 by T of sum I equal 1 to T LDI A Sij, we can go out for lunch together. Okay, we will go out for lunch together outside, no problem. Okay, so 1/T sum I equal 1 to T LDI ASIJ, this is greater than or equal to, so let's see, LDI ASJ, right? Okay, so let me first write down and then I will explain. So 1 by T I equal 1 to T 1/2P sum of R equal 1 to P, and 1 ASIJ VR is not equal to Fi VR. Okay, why is that, right? LDI we have to track somewhere there. What we had before was 1/K, which is sum of I equal 1 to T LDI ASJ, and this is greater than. Okay, so in place of H, basically I replaced it by ASIJ. Okay, so this is like a fact that we just proved, and in this fact I will replace H by ASIJ. Okay, and I did a sum over I equal 1 to T. Okay, so basically this that we have, the generic result that we have proved here is being used here. Okay, so LDIH, in place of that we have H, we have ASIJ, and we did a sum, so there is a sum 1/T, and hence the right hand side also will have a sum 1/T, and in place of H we have HSIJ applied on VR, and Fi is the same. Okay, we just use this result here. So use this here where H is ASIJ. H is ASIJ, right? Okay. So from there, from here onwards, the second step is interchange of the inequality. So this will be equal to 1/2P sum of R equal 1 to P and 1/T, and sum over I equal 1 to T and 1 ASIJ VR is not equal to, I'm just copying over, right, VR. We interchange the P and the and the T loop, the sum. Okay, so that's clear. Okay, almost there. Okay, just 2-3 minutes, I think. There is a trick in these 2-3 minutes, but I may leave this as in for you to ponder maybe. Then, if not, then I will explain it. So it's not a trick basically. It's easy, but anyway, let's see. So here we have, and then so average is greater than mean. Same thing I'm going to do, and this average is over p. So half you take out. This average over p is greater than or equal to mean over p. So this is greater than or equal to half of mean of r in p, and 1 over t, I equal 1 to t, and 1 a Sij Vr is not equal to Fi Vr. Okay, so this is easy. Average greater than or equal to the mean. Right, so this is the last thing. Okay, so fix some r in p. Now fix some r in p, and we can partition all the functions f1 to ft into t by 2 disjoint pairs. Let us say fi prime. So these are the pairs, right, where we have for every c in C, fic. So you make pairs like this, okay, so that fic is not equal to fi prime c. Okay, if and only if, and only if c equals to Vr. Out of these t functions I have, I partition them into t by 2, and so these are the pairs. So fi, they are made into pair in such a way that they don't match if whenever c is Vr. Okay, it's a binary, right, 0 1, and so half of them will take 0, half of them will take 1.
Seems possible.
Yeah.
And so what is VR?
VR was one of these, right? That was not in your sample, right? V1 to VP, right? So V1 to VP, where so we had this C set, our training data was x1, x2, xm, but here you were allowed many possible out of this, but then there are like, once you have this, then there are like V1, V2, VP that are not shown to you. So you have these FIs defined for these guys for a given distribution, but then for these guys, looking into this, you make a partition of your FIs for which there will be those who match, there will be those who don't match. Okay, so that gives you a so each of these FIs, there will be some FIs which give you 0 prediction, there will be some FI which will give you 1 prediction, and those are the pair that don't match, right? So we can partition like that. For every F, there will be other F which gives the one prediction, right? So we have that, and for such a pair, we must have Sij is, so for such a pair, we must have Sij equals to Si prime j. For such a pair, we must have Sji equals to Sji prime. If it C is yes, That's the point. So that's what you have to notice, that it differs only on those that's not in the excise. Those are the V. Okay. So on these training data, they x1 to xm they match. So Sij, Si prime j. So essentially this. So if this is the case, then we can claim. Are you okay with this, like Sij, or you need more? So I can explain this if you want more next time maybe. So then this implies 1a Sij Vr is not equal to Fi Vr plus 1a Si prime j Vr is not equal to Fi prime Vr, must be 1. Okay. So what does this mean, right? This means that either it will be captured by Fi, or it will be captured by Fi prime. Okay, because so for a given Vr, okay, either it will be, because it's a binary 0 or 1, so either it corresponds to Fi or it corresponds to Fi prime. Okay, so hence if this is 0, this must be 1. If this is 1, this must be 0. Yeah. So we may go over this again in the next class, but let us today. So which gives 1 over t, I equal 1 to t, 1 a Sij Vr not equal to Fi Vr to be half. Why is that? This is because there is half of the instances where it's going to give you 1, and other half, because of the other pair, will capture the other half. So these Fi's, which the summation goes from 1 to t. Okay, either you see it from here or you can see it directly from here. I'm saying that Fi's are the pairs, half. For half of the time it's going to be correct, and half of the time it's going to wrong. So in this t sum, t by 2 times is going to be 1. So then it will be 1 by t by 2, which becomes half. Okay, so this can now be used in the claim that I wrote. So this can be used in the claim that I wrote, and then you have half times half, and then you have because in the previous where was that? Yeah, here. So we are here, right? So this is half. Okay, so minimum of is a constant half. So half times half. So this is 1 over 4. Okay, and that's the 1 over 4 that we said in the beginning we claimed, right? So all this until here, and this is half. Overall, it's 1 over 4. So that's more or less the proof. Okay, you are guaranteed to make an error of at least 1 over 4. There is a little bit of equivalence to go to the main statement of the theorem. We can do this in the next class, but that essentially proves the no free lunch theorem. Okay, so let us take some time to go through this, like offline, like you try to see whether you understood this or not. It may not be easy at first step. You do this, and next time you can ask me questions, and specifically we will discuss points where you didn't understand. Okay. Okay then. Okay, let us stop.